So I'm Captain Sagoon, the project manager of CNS2. Today's presentations will be about fractals. First team coming up is Riley's team. We'll be talking about nature.
Alright guys, so first I'm going to cover the Fibonacci sequence, and after that Riley will talk about in nature, as well as Katie will talk about feathers and animals, and coastline and earth. So first I want to cover, get to my next slide real quick. Alright, so the golden ratio is A plus B is to A as A is to B, right? So why is that? Well, I will show you. Alright. So the Fibonacci sequence goes like this: 1, 1, 2, 3, 5, 8, 13, etc. until infinity, right? So we want to figure out a formula that would give us the golden ratio. So if we assign, for example, n equals 0 for, and so on, n equals 1, n equals 2, n equals 3, and so on. And let's use, for the sake of the equation, we'll use f for Fibonacci. F of n is equal, and if we want to find out, for example, the thousandth term, we will need the 998 and 999. So let's use r for any number to the power of n. And plug these in right here. So f of n minus 1 is equal to r to the power of n minus 1. And f of n minus 2 is equal to r of power of n minus 2. So what we have here, 3 points. It might look familiar if you're experienced in math, which is the quadratic formula, which is x squared plus bx plus c is equal to 0. So what we want to do is write this equation as following: r of n is equal to r n minus 1 plus r n minus 2. So now what we want to do is get everything to the left side of the equation so we can set it to equal to 0, just like the quadratic formula. So what we're going to do here is divide everything by Rn, and then that gives us Rn over Rn is just 1. So 1 equals R negative 1 plus 1. So now, we're pretty close, but we got to move everything to the left. So what we have to do is minus 1 minus R. That gives us 1 minus R minus 1. So we're pretty close. Now we can set it equal to 0. What we do next is so we minus 1 minus r, we get 1 minus r minus 1. And then, let's see here. So I did wrong here. Give me 1 second.
Where's it go?
So R of n is equal to R. That's 1 equals R minus 1 plus R minus 2, which is just 1. So now with the minus R minus R, right? That gives us 1 minus R plus 1. So now what we can do is plug this equation into the quadratic formula. But first we want to find out the actual quadratic formula, which is R equals negative B plus or minus square root of b squared minus 4ac all over 2a. And here, our b is negative 1. So we plug in negative 1 and then plus or minus square root of -1 squared minus 4. Our a is 1 and our c is -1. And then this is all over 2a, which is just 1. So this is what we have here. And if you simplify this, this would just give us r equals 1 plus or minus. Negative negative is a positive, and then negative times positive times negative is plus 4. So that's square root of 5 over 2 times 1, which is 2. So this is what we have here. These are both of the forms, both negative and positive. And let's see here. To split those up, our R1 would be 1 plus square root of 5 over 2. And then our R2 would be 1 minus square root of 5 over 2. And if you were to put this in a calculator, it would give you 1.61803. The negative would give you the difference, which is 0.61803. And this is how this correlates to the Bowman ratio. And we can see these in shells, and as well as our galaxy, molecular galaxy, pretty much everywhere. And oh yeah, we have a graphic presentation that Katie was nice enough to bring from Florida, so if you guys want to pass it around and take a look at the show. And Riley, will you take notes? Oh, sorry.
My name is Botan. I'll try not to take up too much of your time. Fractals, as we know, are reoccurring geometric attributes. You can see it here in mountains. Mountains are created when tectonic plates push up against each other and erosion pushes them down and erodes by water and other chemicals over time. You can see here, what's interesting, I hope you can see this, around the second iteration of a mountain, the tectonic plates push upward to the sides and erosion from the other sides, and it continues onward like that. And it creates rivers, which are also fractals, and rivers are created when snow and water run down the mountain and into the ocean. So, next one.
Okay, so I'll talk about hurricanes. So this is a hurricane which follows the Fibonacci sequence, and I'll talk about how hurricanes are formed. So here is the top view of the Earth, which spins counterclockwise, and the Coriolis effect means water from the equator has more momentum going around because it's moving way more, it has to cover more distance. So what this means, it would push the hurricane this way, and it would overpower the winds from the north, creating a counterclockwise in the northern hemisphere. And the opposite happens on the southern hemisphere. The hurricane spins clockwise. So next I'll be talking about the coastline paradox. Here is the island of Ireland, where Riley's from, and I used measurements of 100 miles to measure around Ireland, and with that I got 723 miles. But when I use a smaller radius or a smaller measurement, such as 10 miles, I went around it about 100 times, which gave me 999.99 miles. However, when I go to even deeper, like 1 mile radius, I found that the whole coastline of Ireland is 1,792. So this is basically a fractal. So here's an image or a GIF which shows the deeper you go, the more complex the coastline actually gets, and the longer the coastline will be.
All right, so I'm talking about flowers, playing fractals. Do you guys like pineapple? Does anyone here like pineapple?
Yeah.
Yeah, it's pretty dang good, right? So in order to understand this, you need to know what a fractal is. A fractal essentially is a repeating pattern. It's also known as a dynamic system or moving process, meaning that the further out you go from an object, the more it has to move in order to keep creating the larger image, right? So if you look over here at the pineapple, if you were to just look at the body of the pineapple, it actually resembles the stalks coming out of the plant, as well as the stem from the pineapple, which is in direct correlation with the pattern. And I found a really interesting quote from the video that we watched. Think not of what you see, but what it takes to produce what you see. And the way I look at this is, honestly, I remembered a quote from Transformers, which means there's more than what meets the eye. And I can relate that to patterns as well, meaning that, for example, if you looked at the flower for a sense, if you look at just the center, and it has a very circular motion with the petals, the further you go out from it, the more it resembles itself. And you can see the same thing with this picture of the flower as well. Next slide, please. And for here we got tree fractal, right? So I went on a nature walk this morning, found part of a tree, and it resembles this. So this diagram basically is just showing you the different parts, different segments of the tree, if you will, that they are in fact equal to each other. Meaning that if you were to take, this is B right here, if you were to take BC plus CD, you would in fact get the same distance from B all the way down to the trunk of the tree, or A. And in correlation to, you also have mother branches which stem off into daughter branches, meaning that self-similarity, which is pattern branches, it resembles itself. So if you were to look at this tree right here, if you were to imagine that this was a tree, not an actual branch, if you were to just take this entire segment, it resembles a tree in itself. It has its own mother branch and its own daughter branch, which resembles, the branch itself. It directly correlates to what the tree is. And I related this to fractal code, meaning that in a biological sense, the larger an item can get, such as a tree, for example, the more it actually has to branch out from itself. And you can see this in scientific or biological terms, if you will, such as arteries or veins, which are in humans, as we all know. And this is just showing you more examples of as the bigger the tree grows, the more it has to branch out, as well as the plant. It has the same pattern the farther you go in. You zoom out, it has the exact resemblance.
All right, now that we have talked about fractals in living organisms, like plants, talk about fractals in animals. I looked into feathers more, and I noticed that this is the red-legged partridge. And if you look at the chest here, you'll see this black and white complex fractal pattern going on in there. And so, the size and the shape and the complexity of the overall, pattern is identified as a fractal dimension. So, what do these fractals tell us? What can I say? So, this determines the health of the partridge. Recently, there were researchers researching these red-legged partridges, and they noticed that the pattern on the partridge's chest really affects the immune system of the partridge. Let me elaborate on that. So, researchers decided to put a group of female and male partridges on a diet. So they restricted food for them. And so they put them on that diet for a few weeks, and they noticed a huge difference in the shape and basically the fractal dimensions on the partridge's chest. As you see here, this is a healthy partridge. You see here, the fractals are more connected, they're more symmetrical, all that stuff. Here, they're not connected as much. The patterns are not as complex. So yeah, this affects, partridges choosing mates for reproduction and the overall health. Next is, I noticed a really cool pattern going on with the peacock feather. As you see here, the peacock feathers have the structure. First, it starts off with a shaft. The shaft branches off, it projects into a thing called a barb. And from that barb, it branches off like a tree into a barbule. And from there, it gets more complex, but from that barbule, it basically branches off into a booklet. This is the overall shape of the peacock feather. You know, if you like use a microscope to zoom in to these, you know, beautiful, intricate fractal patterns on the, you know, peacock feather, you will see these shapes repeating more and more. So yeah. And this is what happens when you triple acid. This is the end for us. Thank you.